I am Biju Balakrishnan working with SIS GST, and the topic I am going to explain sampling theorem for low pass signal. Basically in many applications the information signal is in the form of analog signals like output of microphone, output of video camera, but nowadays we want to convert that analog signals to digital signal. So there are many digital processing applications are possible on information signal. The better quality can be achieved using the digital compression techniques, digital processing technique. So that is why the requirement is analog signal should be converted to digital signal. Then the information can be transmitted in the form of digital signal. At the receiving side, better quality can be achieved. And the first step for converting analog signal to digital signal is continuous time signal should be converted to discrete time signal. For that, we need sampling theorem. The meaning of sampling is the input signal is converted to a discrete time signal. So basically it can be implemented using a switch. Switch is going to be closed at every sampling interval. Maybe we can say it's a TS second. So at every TS second, switch is going to be closed. Whatever be the input, that input will come at the output side. So the continuous time signal can be converted to discrete time signal. But now the question is, how many samples should be taken per second? And that is going to be decided based on our sampling theorem. And here the sampling theorem is explaining for a low pass signal, and the meaning of low pass signal is the frequency is varying from 0 to FM. And input signal may not be a low pass signal. So what we want to do first, the signal should pass through a low pass signal with a cutoff frequency FM. Then the frequency is varying only from 0 to FM and the bandwidth is FM Hertz. So we can say it's a low pass signal with a cutoff frequency FM Hertz. So that is why first the signal is passing through a low pass filter with a cutoff frequency FM. Normally for a voice communication, especially in a telephone communication, the cutoff frequency FM is equal to 3.4 kilohertz. According to sampling theorem, x of t be a band limited signal with maximum frequency FM, that is the meaning of a low pass signal. X of t can be represented as x of nts, and that nts shows that the signal is not a continuous time signal, it's a discrete time signal existing only at every ts second using a periodic train of impulses. And the meaning of the periodic train of impulses, the signal is going to be taken only at every ts second without any width. Practically it is not realizable, but theoretically we are saying the signal is going to be implemented using periodic train of impulses. This process is called instantaneous sampling. If you are using periodic train of impulses, then the sampling is known as instantaneous sampling. Instead of that, periodic train of pulses are going to be used practically. The reason is when the switch is going to be closed, it cannot be closed for a 0 second. So it will take some finite time. Due to that reason, instead of getting instantaneous sampled signal, we are getting practically pulse amplitude modulated signal. From x of nts, x of t can be regenerated, that is at the receiving side. From the sampled signal, x of t can be regenerated without any distortion using an LPF with cutoff frequency FM Hertz, where FM is the maximum frequency of the input signal, provided. Now the condition is Fs should be greater than or is equal to twice FM. That means the number of samples we should take per second should be greater than or equal to twice of maximum frequency of the input signal. Where FM is the maximum frequency of the input signal, Fs is a sampling frequency, 1 upon Fs is Ts, that's a sampling interval. So at every Ts second, switch can be closed, that input will come at the output side. We are converting that x of t into x of nts. From x of nts, original signal can be regenerated without any distortion if we are able to get at least twice FM samples per second. Here I am showing the same process in time domain. The input signal is multiplied with a periodic train of impulses. Input signal is x of t, periodic train of impulse is s of t, and the product is x of t into s of t. This is known as instantaneous sampled signal. That closing, the switch is going to be closed at every ts second, can be expressed in terms of a multiplication. So that is x of t into s of t. That is the instantaneous sampled signal. And from this instantaneous sampled signal, original signal can be regenerated using an LPF with a cutoff frequency FM Hertz. This LPF is known as reconstruction filter. This reconstruction filter is used at the receiving side. Now I am proving the sampling theorem in frequency domain. X of t is the input signal and its Fourier transform is x of f. S of t is a sampling signal, that is a periodic train of impulses, and the Fourier transform 1 by ts sigma del f minus nfs. And x of t and s of t are multiplied in time domain, that is x of t into s of t. Multiplication in time domain is equivalent to convolution in frequency domain. That is why x of f convolution with 1 by ts sigma del f minus nfs, and the result is 1 by ts sigma x of f minus nfs. And this is a Fourier transform of instantaneous sampled signal. And n is varying from minus infinity to plus infinity. When n is equal to 0, it will be x of f. N is equal to 1, x of f minus fs, that will be the right shifted spectrum. N is equal to minus 1, x of f plus fs, that will be the left shifted version. Like that we are going to get the spectrum. So here I am going to take 3 different cases. That is case 1, sampling frequency fs greater than twice fm. Case 2, fs is equal to twice fm. Case 3, fs less than twice fm. So finally we should be able to prove the result that fs greater than twice fm and fs is equal to twice fm. Original signal can be regenerated without any distortion. Case 1 is fs greater than twice fm, and this sampling is known as oversampling because we are going to take more number of samples after closing the switch at every ts second. And the result is 1 by ts into x of f, that is when n is equal to 0, and next when n is equal to 1 by ts into x of f minus fs, and the condition here is fs greater than twice fm. That is why there is a gap between first spectrum and second spectrum. This is the guard band between x of f and x of f minus fs, and this is due to fs greater than twice fm. And from this spectrum we are able to get the original spectrum, that is a message spectrum 1 by ts into x of f, if this is passing through an LPF with a cutoff frequency fm. So once it is passing through LPF with a cutoff frequency fm, the output is only 1 by ts into x of f. That is always same as the original spectrum x of f. The reason is x of f is multiplied by a constant, the information remains same. This indicates that if the condition is satisfied, that is fs greater than twice fm, original signal can be regenerated without any distortion using an LPF with a cutoff frequency fm. Case 2, fs is equal to twice fm, and this particular rate is known as Nyquist rate. That is the minimum number of samples needed to get the original signal without any distortion. Even under this case, we can see there is no overlap between x of f and x of f minus fs. So due to this reason, if it is passing through an LPF with cutoff frequency fm, only 1 by ts into x of f can be regenerated at the output side. That is exactly same as the original spectrum. This shows that original signal x of f can be regenerated without any distortion if fs is equal to twice fm. So that's an indication. If fs is equal to twice fm or fs greater than twice fm, original signal can be regenerated without any distortion. So I'll go for case 3. Case 3, fs less than twice fm. When fs less than twice fm, that particular rate is known as undersampling. So due to fs less than twice fm, there is an overlap between x of f and x of f minus fs. Surely you can see that overlap here. This is that overlap area. X of f and x of f minus fs are overlapping. Due to this overlap, and there is a distortion between the spectrum x of f and its shifted signal x of f minus fs. And if it is passing through an LPF with a cutoff frequency fm, the output what we are going to get is from minus fm to plus fm. So from minus fm to plus fm, we are getting x of f, but the part of x of f minus fs and x of fs is overlapped with x of f. Due to this overlap, there is a distortion occurring at the output side. This distortion is known as fold-over distortion, or that is also known as aliasing distortion. The reason is the distortion is generated by the alias of x of f. X of f minus fs, it's a alias of x of f, and x of f minus fs is creating distortion with the x of f. That is why it is known as aliasing distortion. So again, this indicates that when fs less than twice fm, original signal cannot be regenerated without any distortion. So we are able to conclude like this: if fs greater than or is equal to twice fm, original signal can be regenerated without any distortion. If fs less than twice fm, signal cannot be regenerated without any distortion. But practically, when you are going for a practical sampling technique, when fs is equal to twice fm, original signal cannot be regenerated without any distortion. The reason for that is, when fs is equal to twice fm, we need an ideal low pass filter. But ideal low pass filter is not a realizable filter. Due to that reason, practically fs is always greater than twice fm. For a music conversion, the maximum frequency normally we are going to take is 20 kilohertz, and the sampling frequency is equal to 44.1 kilohertz. For telephone communication, maximum frequency is equal to 3.4 kilohertz, but the sampling frequency is equal to 8 kilohertz. So for all practical application, fs is always greater than or is equal to twice fm. So this is the proof of sampling theorem.